the force between two parallel currents which are very long, infinitely long, say. I have two conductors here, these two, they too carry currents. The current in the first conductor is I1, the current in the second conductor is I2, and the distance of separation between them is R. Now, I can calculate the force between them. The force between them turns out to be mu naught I1 I2 divided by 2 pi R into L, where L is the length I consider. Suppose L is the length I consider, this is the length. As they are infinitely long, I cannot consider the complete wires. I consider a part of it, I consider L part of it, that is the force. But sometimes the other thing turns out to be very useful, that is called force per unit length, small f. That is force divided by length. If I divide F by L here, I divide L by here. That gives me mu naught I1 I2 divided by 2 pi R. That is a force per unit length between two parallel conductors. This you know the formula. This is an important expression which is used to define ampere. Now, here you need to consider one more point. Suppose I have two conductors like this, they carry current in the same direction, they are called like currents. These like currents attract each other. Suppose I have two currents like this, one is like this, the other is like this, they are in opposite directions, they are anti-parallel. Such currents are called unlike currents, and unlike currents repel each other. That is an important point you remember. Like currents attract and unlike currents repel. Now, let us solve some problems on this idea. In the figure, if the force on the wire Q is 0, the distance d is A 10 centimeter, B 15 centimeter, C 20 centimeter, D 25 centimeters. You can see the figure here. I have three very long wires P, Q and R. The current to the first wire is 30 amp, the current to the second wire is I, and the current to the third wire is 20 amp. It may seem that this wire current to the second wire is not given, actually it turns out to be that is not needed actually. The distance between first two wires is D, the distance between second two wires is 10 centimeter. I need to find the distance D. I am given with the condition that the wire Q experiences no force. Why does not it experience any force? Just because these two currents are parallel, therefore wire P exerts an attractive force on wire Q, and these two currents are in the same direction, therefore they attract each other, therefore wire R exerts an attractive force on wire Q. It is experiencing no force, Q is experiencing no force, just because the attractive force due to P is exactly equal to the attractive force due to R, therefore the net force on wire Q is 0. That is, force on Q due to P is exactly equal to force on Q due to R. If they are equal, anyhow they are opposite, the net force acting on wire Q becomes 0, therefore it does not experience any force. Let us consider a part of the wire like this, L. The force between two parallel currents is given by mu naught I1 I2 divided by 2 pi R into L. Force on Q due to P is given by mu naught I1 is 30 amps into I2 is I into L is length divided by 2 pi into distance is D must be equal to mu naught into I1 is I into I2 is 20 into L is L divided by 2 pi into that distance is 10 centimeter. I do not convert it into meter because if I substitute this in centimeters, the answer comes out to be in centimeter. Now let us cancel what we can cancel, all things we can cancel, mu naught are cancelled, I and I get cancelled. You see here a value of I is not needed, they get cancelled. L gets cancelled, pi gets cancelled. Therefore, D must be equal to 30 into 10 divided by 20, that is equal to 30 into 10 is 300 divided by 10 is 15 centimeter. The distance between these two wires is 15 centimeter. If the distance between those two wires is 10 centimeter, then for these currents, wire Q experiences no force. The correct answer is option B. Suppose we have a current loop like this. The loop has a current I, the number of turns in the loop is N, and the area it covers is A. Then we can define a term called magnetic moment for this loop, that is given by M is equal to N into I into A. Magnetic moment is the product of number of turns, current and area. SI unit is amp into meter square, that is SI unit. Magnetic moment is a vector. The direction of magnetic moment is again denoted by, again given by screw rule. For example, in this case the current is clockwise. I keep a screw here, I rotate it in the direction of the current, the screw goes inwards. Therefore, for this loop we have considered the magnetic moment is into the loop. That is, for clockwise currents the magnetic moment is into the loop. For anti-clockwise currents, the magnetic moment is away from the loop, that is towards us. Let us solve some problems based on these ideas. Find the magnetic moment of the loop in the figure. The loop is here. The options are 4IL square, 2 root 2 IL square, 2IL square, 4 root 2 IL square. The figure is here. It consists of two parts, this part and this part. This part lies in the YZ plane and this part lies in the XZ plane. It is a rectangle actually. The length is L, breadth is 2L. Its length is L, breadth is 2L, the current is same. Now I can separate these two parts. This part I will write here, that is this one. The length is 2L, the breadth is L, the current is anti-clockwise, current I. This lies in YZ plane and this one I will write here, that is something like this. That lies in XZ plane and the current is again like this. The current is I, this length is L, that length is 2L. Now I will calculate magnetic moment due to this first part, magnetic moment due to this second part, and I add them. Magnetic moment due to first part is given by current into area. Area is 2L into L, that is 2L square, that is equal to 2IL square. It lies in YZ plane and the current is clockwise. Therefore, the magnetic field would be pointing into the board, but out of the board direction is x axis, into the board is minus x axis. Therefore, direction is minus I cap. Magnetic moment of second part, this one is exactly same because length is same, current is same. Therefore, by magnitude it is 2L square again, but the direction is clockwise again, the direction is clockwise. Therefore, magnetic field would be pointing into the board, but upward is y axis, therefore downward is minus y axis, therefore this becomes minus j cap. Therefore, net magnetic moment M is equal to M1 plus M2, but M1 and M2 are equal, they are equal except for these two unit vectors. Therefore, I can write minus 2L square I, that is a common factor among these. What remains is I cap plus j cap. I am asked to calculate the magnitude, therefore, I can skip that minus sign. What remains is 2L square I into magnitude of this one is square root of 1 square plus 1 square, that is square root of 2. Therefore, the answer is 2 root 2 IL square. The correct option is B, 2 root 2 IL square. Let us learn the applications of Ampere circuital law. Ampere circuital law states that the closed line integral magnetic field over a closed loop is equal to mu naught I enclosed. Here is a figure. This is a loop for which I am going to apply Ampere circuital law. The loop for which I am going to apply Ampere circuital law is called an Amperian loop. This loop is an Amperian loop. According to Ampere circuital law, now closed line integral B dot dl is equal to mu naught I enclosed within the loop. There are three currents enclosed within the loop. I4 is outside, it is not counted as enclosed current. These three are enclosed currents. I write I1 plus I2 minus I3. Minus I3 because that is in opposite direction. This is how we use Ampere circuital law. Although Ampere circuital law works for any case for static magnetic field, it is not very useful to calculate magnetic fields always. It becomes very useful when there is symmetric situations like infinitely long wire or a solenoid or a toroid, etc. As an application of Ampere circuital law, let us solve a problem. The current density in a straight uniform wire of radius r varies with the distance r from the axis as J of r is equal to kr square. The magnetic field at distance s less than r is 2 mu naught ks cube, 2 mu naught ks cube by 2, mu naught ks cube by 4, 4 mu naught ks cube are the options. Now, I have a wire like this. The radius of the wire is r. This is the axis. At this distance r, the current density varies with distance as kr square. The current density here would be kr square. You know, current density is current divided by area. Now, I have to find the magnetic field. As there is cylindrical symmetry, I can easily use Ampere circuital law. Let me use Ampere circuital law. Ampere circuital law states that closed line integral B dot dl is equal to mu naught I enclosed. That is Ampere circuital law. Now, suppose I look at the wire from this side, that is the center O. I have to find the magnetic field somewhere here at point P at a distance S. It is given that S is less than R. From this point I draw an Amperian loop. This is the Amperian loop. To calculate mu naught I enclosed, I have to find the current within this wire. But because of cylindrical symmetry, if I am worried about the left hand side, B and DL are exactly tangential everywhere. That is one point here. Therefore, BDL cos theta would be BDL. And as there is cylindrical symmetry, B would be same everywhere on this surface. Therefore, LHS of Ampere circuital law, which is closed line integral B dot DL, would be just B integral dl, closed integral dl, which is equal to B into 2 pi s. That is the length of this Amperian loop, B into 2 pi s. That is the LHS of Ampere circuital law. Let me call this equation number 1. Let me calculate the right hand side. Right hand side mu naught into I enclosed. First I have to find I enclosed. To find I enclosed, I take a patch here, it is a very small patch at a distance x from the center and thickness dx. That is a patch, a circular patch of thickness dx and distance x. The area of that one is, area of that patch is 2 pi x dx. Area of that patch is 2 pi x dx. Therefore, current flowing through that wire, that patch is given by di is equal to current density into area, that is j into 2 pi x dx, that is equal to, but j is kr square, therefore k x square, because the distance is x, into 2 pi x dx, that implies di is equal to 2 pi k x square into x is x cube dx. Therefore, current enclosed would be integral of di, where x runs from 0 to s, because this is the first patch and this would be the last patch, 0 to s, that is equal to integral 0 to s 2 pi k s cube dx. That gives us, if I integrate this one, 2 pi k s power 4 divided by 4, when I integrate that one, that gives me k s power 4 into pi divided by 2. Therefore, right hand side would be, RHS would be mu naught I enclosed, which is equal to pi k s power 4 mu naught divided by 2. By applying Ampere circuital law, I get, by applying Ampere circuital law, I mean I have to equate left hand side and right hand side now, it gives me B into 2 pi s is equal to pi k s power 4 mu naught divided by 2, which gives you B is equal to pi gets cancelled, one of the k s gets cancelled, 2 cross multiplies, k s cube mu naught divided by 4, k s cube mu naught divided by 4. The answer is C. As an application of Ampere circuital law, we can calculate the magnetic fields of a solenoid and a toroid. If you have a long solenoid, very long, very thin, a long thin solenoid, the magnetic field well inside it is given by mu naught Ni, where N is called number of turns per unit length, that is given by capital N divided by L. N is number of turns divided by length, number of turns divided by length, mu naught Ni. The magnetic field due to a solenoid depends on the current, it depends on the number of turns, and it depends on the length of the solenoid. It is assumed that there is nothing inside the solenoid, that is either air or vacuum is inside it. If there is something inside the solenoid or the toroid, then you should replace nu naught with nu. Nu is nu naught nu r. Nu r is called relative permeability of the medium. That can be anything for ferromagnetic materials like iron, mu r can be very large, of the order of 1000. If you have a finite solenoid, this is for a very long solenoid, very long thin solenoid, but if you have a short solenoid, larger one, I mean larger in diameter, suppose this is the case, the number of turns per unit length is even now n. You are calculating the magnetic field somewhere here. As shown in the figure, theta 1 and theta 2 are the angles made with these two lines with the axis of the solenoid. Then the magnetic field here is given by mu naught Ni by 2 into cos theta 1 plus cos theta 2. If you have a very long solenoid, this gets, I mean like this becomes very parallel to the axis, and theta 1 and theta 2 reduce to 0. That gives you cos 0 plus cos 0, that is 1 plus 1 2 gets cancelled, that reduces the same formula. If you have a toroid, The magnetic field inside the toroid is given by V is equal to mu naught Ni, again the same formula, but the difference is that mu naught Ni by 2 pi r, because toroid is a circular shaped ring, therefore length of the toroid should be 2 pi r. Here there is L, here there is also length, but the length of the toroid is 2 pi r. These are the formula to calculate the magnetic fields of a solenoid and a toroid. Let us solve some problems on these concepts. Here is the problem. A long solenoid carrying a current produces a magnetic field B on the axis. If the current is doubled and the number of turns per centimeter are halved, the new magnetic field is, the options are B, 2B, 4B and 0.5B. It is about the magnetic field of a solenoid. Magnetic field of a solenoid B is given by mu naught Ni, where mu naught is the permeability of free space, N is the number of turns per unit length and I is the current. Now, suppose the current is I and number of turns is N, therefore the magnetic field now inside the solenoid is mu naught Ni. Now, the current is doubled, that is new current is equal to 2 times old current, and number of turns per unit length are halved, therefore new number of turns is equal to old number of turns divided by 2. I have to find the new magnetic field, which is equal to mu naught into new number of turns into new current, which is equal to mu naught into new number of turns is N by 2 into new current is 2I. These two 2's get cancelled. I am left with mu naught Ni. That is exactly equal to old magnetic field. Therefore, the new magnetic field is equal to old magnetic field B. The answer is option A.